Hello everyone, I welcome you all in this. Hello everyone, I welcome you all in this session of thermodynamics. This is the part 2, and in this session we will discuss about the second phase, that means your first law of thermodynamics. Okay, this is your first law of thermodynamics. So in this part, today is the last part of the first law, and we will discuss. See, the first law we already discussed that the first law is applicable for in these three situations. First, closed system; second, open system; and third one is the open with unsteady situation. Okay, so today we will discuss the application of the first law for open and the open system with unsteady state. So my dear, as you know that the many engineering device is your steady flow device, and some devices of practical devices is your unsteady devices. So we will discuss all the things of this related to that, and also we already discussed that what is your displacement work, and what is the consequence of this displacement work when it is applied, and what is the limitation of that equation. Okay, so there is a very important conclusion is that sir, this equation is applied for the non-flow situation. That means there is a no flow across the boundary. It is not like that that is your closed system or open system. Non-flow is the second thing and closed system is the second thing, another thing. So it is your non-flow work. It is not a closed system work. Number first. Number second, it is your internally reversible work. It is not a reversible work. So, and this is applicable only for the quasi-equilibrium process. This is applicable for the quasi-equilibrium process. So like that we already discussed and how to derive this equation. Okay, so all the things we have. Now then we have to discuss about that what is the meaning of this equation. That means work done due to the displacement of a moving boundary for a simple compressible substance undergoing a quasi-equilibrium process. Okay, and that is called displacement. Where is the displacement of a boundary takes place? But the second condition is that displacement against the resistance. So this is your diagram over we have to under which we have to verify that your statement. See, this is your completely vacuum. That means there is no any pressure. The second part. So if there is gas, it will expand. There is no any work. That is called free expansion. We will discuss in the detail in second law of thermodynamics. Now we have to apply the general condition of that PV power gamma for the polytropic, isothermal, and also there is a constant pressure process. So we have to discuss, and what is that? We have to conclude that the constant pressure, the area under the curve of a constant pressure is higher than area under the curve. This is what we are. This second B is your what? Isothermal. Then there is a adiabatic. So there is a expansion. Where is the expansion is there? This is your expansion. Expansion will take place. This is your expansion. So constant pressure expansion have a more area as compared to the polytropic process. With this example, we can easily understand in the previous section. Now, we also proved that all the isothermal process must be a reversible process. No, it is not like that. Isothermal process, yes, isothermal process not must, maybe reversible process, but it is not must. We already discussed like that in the previous section, and also we have to end up here in the previous session. We have to end up here. What is that? All the slow process must necessarily be the reversible process. This is whether true or false. Anyone please reply in the comment box. This is true or false. All the slow process must necessarily be reversible. This is true or false. So we have to also prove that no, it is false. It is the false statement. It is the false statement, and we also discuss this. What is the conclusion of this one? Okay, now we have to discuss the first law, but before that we have to discuss with the concept of energy. Concept of energy. What is that concept of energy? See my dear, if you think about the energy, what is your energy? So you know, you are aware with the term of this energy from the childhood. So what we have generally in the classical mechanics, the energy is a kind of mechanical energy, but that is the form of that energy. Okay, so if we talk about that according to thermodynamics, so this says that energy can exist in the numerous forms such as thermal energy, mechanical energy, kinetic energy, and the potential, electrical, magnetic, chemical, nuclear, and their sum, all their sums. Here is one thing is very important. If you talk about the kinetic energy and potential energy. So my dear, please tell me, if someone asks you, what is the kinetic energy and potential energy? It is their energy, and energy associated with the two terms, that is, one is the macroscopic, other is the microscopic. Right. Good evening, beta. Good evening, Mani. Good evening, beta. One is your microscopic and other is the microscopic energy form of energy. So thermodynamics first energy says that this energy have a two category. First one is the macroscopic, second one is the microscopic. Macroscopic, it is a potential energy and kinetic energy. This is a microscopic form of energy. Very important, I'm telling you. So someone asks you the potential energy and kinetic energy, which form of energy? Macroscopic form of energy, that is potential energy and kinetic energy. Now second one, another form is the microscopic. See beta, micro, you know that is associated with the molecules of the system. So it is either in the form of translational energy, rotational energy and vibrational energy. So here is the confusion in mind. Sir, if the molecules have a translation, that means if kinetic energy, yes. So just now you already told that sir, kinetic is a microscopic, but why it is in the micro form? Why? Because beta, see, kinetic energy, if someone asks you, you can easily tell sir, this is a macro form of energy. But it is not like that kinetic energy always it is also present in the micro level. In the micro level. So translational energy, rotational energy, vibrational energy, these are associated with the strong function of temperature of the system. If you increase this temperature of the system, molecules maybe translate more, maybe rotation, maybe vibration. So it associated with the kinetic energy and also it associated with the potential energy. We will discuss. Okay. Now, so what is that? Energy can exist in a numerous forms such as thermal, mechanical, kinetic, potential, electrical, magnetic, chemical, nuclear, and their sums. Now, and that the total, that means if you sum of all this energy, that is called E, energy of the system. E is the energy of the system. E is called energy of the system. Now, my dear, the sum of all the microscopic, that means this microscopic plus the sum of all the sum of all the micro, that means if you add this all energy. Now the very important thing, if you add all the microscopic form, not we are talking about not macro, we are talking about micro. So if you add all this energy, that is called the internal energy of the system, U. So E is the energy of a one component is U. And U is associated with the microscopic form of energy, that is called internal energy. Internal energy. So internal energy, it is the energy which is in the form as a microscopic level, and it is constituted with the translation, rotation and vibration. Okay. Now the total energy E. The total energy E of a system consists of a kinetic energy, potential energy and internal energy. That means this total energy E is the sum of macroscopic energy and microscopic energy. So energy of the system, it is a energy contained with the summation of microscopic and macroscopic. Microscopic energy which is presents in the system, that is in the form of internal energy. And internal energy have a further classification, that means your translational form, rotational form, vibrational form, it is like that. So the total energy of the system, E, it is the sum of microscopic plus sum of macroscopic. This is your macroscopic form of energy. Microscopic plus sum of macroscopic form of energy. Now, beta, in generally, when we analyze the thermodynamics, in generally, we can neglect this macroscopic form of energy. Please tell me, when we have to neglect this macroscopic form of energy? When the system is stationary. when the system is stationary. When the system is stationary, the kinetic energy change and potential energy change is zero. It is not like that kinetic energy and potential energy. Why? Because energy we cannot bother about in the absolute sense. We can bother only about the change form. Initial to final state, that means it is a change. So change in kinetic energy and change in potential energy in generally we have to neglect in the thermodynamics analysis when the system is stationary. When the system is stationary, right? Okay. So what is the conclusion of this slide? The conclusion of this slide beta that energy is the total energy of the system, and this total energy of the system is sum of the microscopic form of energy plus macroscopic form of energy. Microscopic form of energy is a constituent with the translation due to the translation, vibration and rotation, and that is associated with the internal energy of the system, right? And macroscopic form of energy, it is in generally kinetic in a form and potential form, and the macroscopic form we have to neglect when the system is stationary. When the system is stationary, that is clear up to that one. Is there any confusion in this slide? Please ask me. Is there any confusion in this slide? Please ask me. You may ask. I am very happy to reply your comment. Okay? This is okay? Now, next one. There is some observation. This is a typical figure which is we have to intentionally placed here. Why? Because many times in the interview they are supposed to be asked. What is that? Does the glass of water which is sitting on the table, does the glass of a water sitting on the table have any energy? You can say that yes or not. See my dear, this glass have no energy, and this glass have energy. That depends upon the level, on which level you have to study, macroscopic or microscopic. So if no any energy, no apparent energy of the glass of water on the microscopic scale. Why? Because this glass of water act as a stationary system. Stationary system. This is your stationary system. That means this is at a fixed position. Okay, the potential not change, the kinetic of the movement of the glass is not there. So this is a stationary system. That means this glass delta Ke and delta P is 0. That means the glass have an energy E in which there is only U. There is only U form of energy, other form of energy is 0, change. Now, so you can say that, sir, in the glass, if you take any portion of the glass of a water that have a two domain. First one is your microscopic. This is your see here, microscopic kinetic energy. So one form is kinetic energy. That is the part of the internal energy. That means what is the internal energy? U. That is one part is the kinetic energy, and that kinetic energy, it is a microscopic form of energy. Second one, molecular attractive. So there is an attraction of the molecules through a bonds. So attractive force are associated with the potential energy. So in this glass, there have a two status of energy. First status is internal, first status is kinetic energy, which is nothing, which is the microscopic kinetic energy, and due to that, what is that? Due to the random motion. So the kinetic energy associated with this system as a microscopic, that is due to the random motion of the molecules. Why the random motion is there? Why? Because there is a thermal agents and thermal energy. That means this glass of water have a certain temperature. So this, due to this certain temperature, this energy will have. And this energy is due to the random motion. That means motion of the molecules at a microscopic level. Now, second one is the molecular attractive vibration. Molecular attractive vibration that are associated with the potential energy. So in this one, there is also kinetic energy, and this one also potential energy. Sometimes internal energy is also called a thermal energy. Internal energy is also called a thermal energy. So mind it beta, thermal energy, it is a form of a internal energy. thermal energy, it is a form of internal energy, and that are in the form of microscopic level. Okay. Now next. So see this one, this figure, this slide is also important. What is this one? See, the portion of the internal energy. Okay, the portion of internal, first say this internal energy U. So this is your internal energy U, and internal energy also called thermal energy. Internal energy also called thermal energy, and is the energy of a substance is due to the kinetic and potential energy. Just now we have to see that, sir, this energy is associated with the kinetic energy and potential energy. So this internal energy is combined with a also known as a thermal energy, is combined with the kinetic and potential, but this is your microscopic level. Energy associated with the random motion of all the particles that makes up. Okay. So internal energy is defined as the energy. What is the definition then? Internal energy is defined as the energy associated with the random or disordered motion of the molecules. So that are measured by the internal energy. So my dear, always try to understand one thing. What is that? Due to the property, see, internal energy is defined as the energy associated with the random or disordered motion of the molecules. Now, if you enter into the second law, there is one property which also measured due to the randomness, known as entropy. And entropy is also a system property. That is also a system property. So what is the difference between, if you talk about what is the difference between here in this sense, I am talking about the sense. What is the difference between this internal energy and entropy? Why? Because both are associated with the random and disorderedness. So what you have to say that? Okay, sir, this internal energy is strongly due to the temperature. That means if the temperature will increase, if there is any adiabatic, so if temperature will increase in adiabatic system, its internal energy increase, also associated with this entropy will increase. So in this one, if you talk about the energy, there is no any generation kind of this thing in thermodynamics. But if you talk about the entropy associated with this molecules, vibration or randomness, there must be a generation. So there must one component extra will add when you have measure the disorderness of the molecules through the entropy. There one term is added by the generation. Okay. Now, so the portion of internal energy of the system associated with the kinetic energy. Why? This internal energy is associated with the kinetic energy and potential energy. So the internal energy which is associated with the kinetic energy of the molecules, that is called sensible energy. That is called sensible energy. That means you have to sense this energy. So internal energy, if you talk about the total energy of the system, in that part there is an internal energy of the system, and that internal energy is a one kind of form that is called kinetic energy, and that kinetic energy is measured by the sensible energy. What is why? Because you have to measure the sensible energy. MC delta T. MC delta T you can measure. Mass of the body, C specific heat, and delta T, that means temperature difference. You can measure, that means this kinetic energy, higher is the higher kinetic energy, higher is the higher sensible energy. Now the second one is the internal energy associated with the phase change. So my dear, throughout thermodynamics, the internal energy have a two status. One is the kinetic energy, other is the phase change. That's it. That means one is the motion and there is a without motion. So in the phase change, the temperature is fixed. So phase change, so that energy associated with the latent, and the second one is the sensible. That means the internal energy that is measured by the measured at the molecular level have a two status. First one is the sensible status, second one is the latent. Sensible energy, who is the responsible to develop this, who is the responsible to associate, who is the associated energy which is the responsible for the sensible energy? That is your kinetic energy. And who is the associated with the latent energy? That is your responsible for the phase change. Clear? That is clear? Okay, beta. Is there any problem up to that one? No. Now next. So if we talk about the balance, now if you talk about the very much aware about the energy, then we have to discuss about the energy balance. What is the energy balance? The energy balance is the net energy change. That means net energy change. And my dear, this net energy change either increase or decrease. This net energy change either increase or decrease. That means this energy may be increase, may be decrease. In the total energy, that means you have, if there is a system, system have energy. System have energy. And this energy of the net change of this energy either increase or decrease during the process equal to the difference between total energy entering, transfer, and total energy leaving of the process. That means if you have any system and system have energy, its change in energy is associated with the energy into the system minus energy out from the system. That difference is equal to delta E. That means energy in minus energy out is equal to change in energy of the system. Now my dear, what is the change in energy of the system? System final energy minus system initial energy. That means this is a point function, stored form of energy. So energy in or out, who is the responsible to transfer this energy? The responsible fellow is heat, work and mass. Who is the responsible to this energy transfer? Heat, work and mass. And who is the responsible to change in energy of the system? The change in energy of the system, it is in the store form, and that is responsible to the internal energy, kinetic energy, potential energy. Okay. Now, this is at rate basis. What is the rate of energy transfer is equal to rate of change of internal energy. Clear? This is clear, excuse me. Now, this is okay. Now, next one. So, what is that? Physically, what they say is that if there is a cycle. So, cycle, physically, what they means? That means if you do the activity according to your cyclic process. So, cyclic process, what is that? If you transfer the cyclic process, thermodynamics energy, what they say is that if you transfer heat to the system, system holds the capacity to do an equivalent amount of work. Yes, if you transfer this, so that is your net. If there is a cyclic process, non-cyclic, you cannot say like that. So, for the cyclic process, what is that? If you transfer the heat to the system during a cyclic process, that all the heat are responsible to do the equivalent amount of work. Okay, equivalent amount of work. Now, my dear, so Q net out is equal to Q net in. You can write like that. If the cyclic integration dQ is equal to cyclic integration of dW. That means you can write like also Q net is equal to W naught, and both are the same sense. Both are the same sense. That means what is the area you have to calculate during the cycle? That equivalent area also measured by the heat transfer. Okay, you can write like that. Okay, we cannot write like that for the process 1 to 2. This is for the cycle. Okay, done. Now next one, see this one example. This one example is there. There is a container. Okay, this is your container, and in this container there is a shaft work. In this container there is a shaft work. So let's suppose this container before stirring the system, its internal energy initially at 800 kilojoule. Now there is a fluid. If you enter this energy, that means if you enter, there is a shaft work. W shaft in. Now, my dear, my question is that, and who is the responsible factor, who is the responsible fellow which is change its internal energy? Let's suppose its initial internal energy U1, and now after stirring the system, its internal energy is U2. So, who is the responsible to change this internal energy? Please tell me. Reply in the comment. Who is the responsible to change this internal energy, please? Who is the responsible factor which is change its internal energy? Please tell me. That is your viscosity. That is your viscosity. So fluid viscosity is your responsible fellow to change its state. U1 to U2. This is a state point. U1 to U2. Now, my dear, if you churning this fluid, the fluid have a viscosity, so there must be a dissipation. So due to this dissipation, that dissipative effect will be responsible to change its internal energy. Yes, U. Change in internal energy. So this dissipation, that means if you apply the work, if you supply the work to the system, that means if you churning the system, fluid have a viscosity that makes up its internal energy change. Why? Because if you supply this energy, that energy will totally dissipated. Now, if internal energy will increase, so that system is non-adiabatic, there must be a heat supplied. So there must be a heat supply 500. So what is this final internal energy? Apply the first law of thermodynamics. Energy in minus energy out is equal to change in energy of the system. What is the energy in here? Shaft work in. What is the energy out here? Q out is equal to change in internal energy. Why? Because this energy U, delta U plus delta KE plus delta PE. So we have to neglect this. Why you have to neglect? Why? Because you have to assume that system is stationary. System is stationary. That means system is not moving. So that change in energy of the system is equal to the change in internal energy. So there is a change in internal. What is the internal energy? U2 minus U1. So you have U1. Put the value, find the final internal. Now, my dear, its internal energy reduced. Why? Why? Because what is the energy you have to supply, and there is a more and more heat will out. So, though there is a churning process, but there is a cooling. So, my dear, you don't say, someone asks you, if there is a container, in that container, if you churning the fluid, it's always heating, always cooling, both A and B, C, we cannot say. What's your option? First option, if you churning the fluid, it is a heating process only, it is a cooling process, it's a both, we cannot say both. Why? Because if you churning it, it may be heated, that means if its internal energy may be increased, its internal energy may be decreased. That will depend on how much the energy will be lost. Clear? This is clear. Now, next one is in the general relation. What is the general relation? See, in generally, what is the first law? This is the first law of a thermodynamics for a process. Q minus W is equal to delta E. So this is your first law of thermodynamics. First law of TD. Number first. What is the number second? What is the number second? This is first law for the, what is the number? For a closed system. For a closed system. Why it is applicable for the closed system? Anyone please comment in the comment box. Why this first equation Q minus W is equal to delta E is applicable for the closed system? Please tell me. Why it is applicable for the closed system only? Please tell me. Why this equation Q minus W is equal to delta is applicable for the closed system only? Please tell me. Please reply in the comment box. Anyone who watching this video, please reply in the comment box why this first equation Q minus W is equal to delta is applicable for the closed system. Closed and stationary. Not stationary. Closed system. Closed system, not stationary. Please tell me. Please tell me why? Because the energy which is transfer, energy in minus energy out, is only in the form of heat and work. There is no any form of mass. Why? Because if you apply this first law equation initially, this energy in or out is energy transfer by heat, work and mass. Energy transfer by heat, work and mass. So if there is no any mass transfer, so this equation is applicable for the closed system. So this first equation Q minus W equal to delta E, what is the limitation? Limitation is, sir, this is the first law for the process. Number second, this is applicable for the closed system. What is the process? This process, this equation is applied for number first option, reversible. Number second, irreversible. Number third, both. Number four, any one. We cannot say. So this equation applies for both process, either reversible or irreversible. No matter about that. Okay. Number second equation. This equation, Q minus W is equal to delta U. This is also the first law of thermodynamics for a process, applicable for the closed system, but the system is stationary. Why? Because delta E, change in total energy of the system, is equal to change in intermolecular, is only for a stationary system. Stationary system. Clear? Only for stationary system. Now, second one, this is per unit mass basis. This is your per unit mass basis. That means if you write like that, Q minus W is equal to MC delta T per unit mass, divide by the mass, both sides divide by the mass. That means if you take a first equation, Q minus W is equal to delta E, divide by the mass, mass. So this is what? Small q, small w, delta small e. So this is your equation per unit mass basis. Now this is in the form of differential form. That means a very small transfer of energy is equal to very small internal energy change. So this delta q minus delta w is equal to dE. So someone asks you, sir, this dq, you can write like that, this delta or notation delta or d pe power cut, any type of the notation you can use, no problem. So dq minus dw is equal to dE. What is the limitation of this equation? Sir, this equation is applied for the first law of thermodynamics for a process. Number first law for a process. Number second, sir, this equation is applied for the closed system. Number third, this equation is for the per unit mass basis. This equation is per unit mass basis. That means energy per unit mass basis. Clear? Now, my dear, this is the very important thing. The second work is their flow work. This is your flow work. Now, my dear, I will ask you. In the previous session, we have to discuss one form of work known as thermodynamics work. That is the boundary phenomena. That means transfer phenomena. P into dV. What is the so this work? First tell me, what is the difference between that work and this work? See, my dear, that work is applicable only for the displacement of a boundary. That means if there is any boundary is there, either closed boundary or either open boundary. Closed boundary, matlab system closed of a boundary, system open of a boundary, that is called control surface. If there is a displacement, that work is applicable, a displacement in a quasi-static manner. So that equation is applicable, and quasi-static process must be an internal reversible process, but reversible process need not be a quasi-static process. This we'll discuss already. Okay. Now, but this work is not like a quasi-static work. It is only due to the fluid motion. If there is motion will take place, if there is any type of motion will take place, either any form of motion, either it will change due to the pressure, any form of, yes, like one thing is that, see, fluid motion have a different condition. Fluid will move due to the displacement of a boundary. Fluid will move due to the pressure difference. Fluid will move due to the gravity. So the movement of the fluid is only pressure. So this flow work is applicable. That means this flow work is associated with the due to the pressure change. If there is a change in pressure due to the fluid flow, there must be this flow work is there. It is not like that the displacement of a boundary or gravity. No, if there is a flow due to the pressure, that work is associated with this one. That's why this work is also will be introduced when you have to derive the Bernoulli's equation. So, my dear, let's suppose there is a channel. In this one, there is a fluid is flowing. So, if you want a continuous, let's suppose different layer, fluid layer not cross section. So, if you want this cross section will enter into this cross section, this fluid will try to push this one. If you want to move this cross section, this fluid will try to push this one. If you want to move this cross section, this fluid want to type of push push of this cross section. That means this is nothing. This is a pushing kind of work, not a displacement kind of work. This is a pushing kind of work. That's why this work is called mechanical work. That's why this work is called mechanical work. But the PDV work is not a kind of mechanical work. Please mind it. So this work is a pushing kind of work. So this is your mechanical form of work. Mechanical form of work. Number first. Clear? Number first. Number second. This work is a property. It is not a boundary phenomena. That means this is a property relation. That means integration PDV is your work transfer, but this is a work stored. If there is a mass, if there is a fluid is there, and if there is a fluid is flowing, the fluid itself have an energy to maintain this pressure difference. That means a flow work or flow energy is the work or energy required to push the mass into or out from the control volume. This work is necessary for maintaining a continuous flow through a control volume. So that means this work is applicable only for the open system. That means it is applicable only for the open system. But that work, integration PDV work, is applicable for the non-flow, and it is applicable for the flowing. That means the fluid must be flow. If the fluid is rest, that means a glass of a water. Just now we have said that a glass of a water, if there is a water is there, this work is not there. Also integration of PDV work, no any type of work is there. Okay, so this is your kind. And second one, this work is measured per unit mass basis. That means work flow work is equal to P into dV. V is the specific volume. That's it. So, and the specific volume is 1 by density, that is P by rho. So P by rho is also called in the fluid mechanics pressure energy. That is also called pressure energy. So flow work, flow energy, pressure energy, all these are the same things, and that is your per unit mass. That means energy per unit mass of the system. Energy per unit mass of the system. Now my dear, what is the mean by this imaginary piston here? That means why it is imaginary piston is here? The imaginary piston, it is like that if you want to move this layer into the control volume, the layer which is just near to this piston, near to this fluid, act as a plunger. And this plunger is try to push this layer into the control volume. So this is nothing, this is a fluid layer which is very nearer to this fluid element, and this element is try to enter into the control volume. So if you want to enter or exit anything continuous, this work must be present. This work must be present. Clear, beta? Now if we derive this equation for the flow work, there is one subtle concept is there. What is that, beta? If you talk about non-flowing fluid, this is your non-flowing fluid. What is mean by non-flowing fluid? Again you have to tell me. Sir, non-flowing fluid, that means displacement of a boundary. Displacement of a moving boundary. Moving boundary. Displacement of a moving boundary is called non-flowing fluid. What is mean by the flowing fluid? What is mean by the flowing fluid? Flowing fluid is due to the pressure difference. Due to the pressure difference. So due to the pressure difference, the fluid is flow, that is called flowing fluid. And due to the displacement of a boundary is called non flowing fluid. So when the boundary will displaced, you can say that any form of, so the energy, that is your E is your energy, and that E is your specific energy per unit mass basis. This is your per unit mass basis. So this energy E have a 3 component of that energy E. E is the energy per unit mass. What is E? E is the energy per unit mass. This E is the energy per unit mass. So this energy per unit mass have a, that means that is called total energy per unit mass. That means if there is a non-flowing fluid, so what is the total energy? Someone asks you, there is a glass of a water, there is a glass, let's suppose there is a non-flowing, that means there is also displacement of a boundary or a glass in the bottle. That means there is a glass, see this one, there is a glass which is at the present sitting on the table. So this is your non-flowing fluid. This is your non-flowing fluid. Or there is a cylinder and there is a piston and the piston will move. So this is your also non-flowing fluid, only displacement of a boundary. So in this both cases, what is the energy of the system? The energy of the system have a 3 part. First one is your internal energy, second one is the kinetic energy, and third one is the potential energy. That's it. This form of U, it is your micro form, and this kinetic energy and potential energy, it is in form of macroscopic. That is called the total energy per unit mass of a non-flowing fluid. Number second, number first. Number second, if the fluid is flow, so what is the energy? Is there same? Number first, is there same or is there differ? What's your comment? Sir, it is differ. Why? Why? Because, see, if there is a fluid is there, either flowing or non-flowing, this energy will there. Yes or not? This energy, your U, V square, G, Z. This energy is there, either fluid is flow or either fluid is non-flow. This is there. Clear? Clear? Now, other component of one energy which is responsible to the flow of the fluid, that will add. That means what is the main subtle concept? Ki sir, energy of a flowing fluid must be higher than the energy of a non-flowing fluid. That's why many engineering devices like a turbine, pump, compressor, blower, expander, anything, that are the flowing fluid device. Why? Because in that component the extra energy will there. Which form of energy? Flow energy. Which form of energy? Flow energy. So, my dear, the total energy consists of 3 parts for the non-flowing fluid and 4 parts for the flowing fluid. So, there are 4 parts is there. And this PV plus internal energy, there must be a property. Why? Because U is the property. PV plus internal energy. U is the property, P is the property, V is the property. So add this one, there is a property, and that property is known as enthalpy. That property is known as enthalpy. So for the non-flowing fluid, U plus kinetic energy, internal energy plus kinetic energy plus potential energy. For the flowing fluid, instead of internal energy, you must put enthalpy. So enthalpy plus kinetic energy plus potential energy. That's it. That is your non-flowing, that is your flowing fluid. So the very important thing is, sir, if the fluid is there, a glass of a water is there, and if the fluid which is flowing, that means if you flow the glass, now you have to flow the water due to the pressure difference. So the flow of water have a larger energy as compared to flow which is at a rest condition. Clear? So that is the difference between non-flowing fluid energy and flowing fluid energy. Precisely, in generally, that is the difference between displacement of a boundary when the fluid boundary will displaced or when there is a fluid movement of the fluid due to the pressure. movement of the fluid due to the pressure, not movement of the fluid due to the displacement of a boundary. So displacement of a boundary have a low energy as compared to the fluid movement due to the pressure. Clear? So here that P into V plus this internal energy, that is called enthalpy H, and this enthalpy also a property of a system. So there is a birth of enthalpy. So in thermodynamics there is a three E's. Three E's: energy, entropy and exergy. These all are the energy form. Energy, entropy, exergy. Entropy somehow you relate with the energy also. Disorderness of the molecules we can measure through the internal energy. Disorderness of a molecule you can measure by the internal energy. Disorderness of the molecules you can also measure by the exergy, but the situations are different. So I hope you enjoy this video. If you have any confusion up to this content part, please free feel to ask me. Please beta, anyone, if you want to ask, please ask. No problem at all. Anything who present, please ask beta. Otherwise today I will end here. Okay? Clear? Now in the next session we will cover some very fundamental problem, one problem, and then we will enter into the transient condition, and then we will enter into the second law. Up to that, okay? Clear? Money? Clear beta? Okay beta. Thank you. Bye bye. Take care.